electricity. Okay, so talking about diffractions, when a wave goes through an opening, like a slit, or when it goes through a obstacle, they diffract. Okay, so what is the meaning of diffraction? Just put it simply, the spreading of waves, right? So here you have an obstacle, the wave comes by, your expectation maybe is like this. The wave goes through the obstacle and then the middle region got blocked, only the side go through. But in reality, this is not the case. In reality, when they go through the obstacle, they diffract, right? So they kind of spread inwards like this. This is like, you can think of it like the trails or the waves behind a boat, okay, like a speedboat moving, and then the waves behind it. It's like this. Or it can be an opening, okay, such as a doorway where you have sound wave propagate through it. So the sound wave goes like this. Expectation is like this. Only the middle section go through, the side got cut out. But reality, this is not the case. Reality, the wave goes through like this, okay? Now, sometimes they ask you to draw this wave. The way you draw the wave is depending on the slit size. Because sometimes we get like a perfect circle. I mean like a circular waves. And sometimes we get like a plane waves. The middle section is like a flat line and then the side is curved. When do we draw this and when do we draw this? You look at the slit size. If the slit size, this one, is the same as the wavelength here, then you get a circular waves. Okay, that means if the slit size is the same as the wavelength, then you draw this. The wave front is circular. But if the slit size is not the same as the wavelength, then you draw a wave that is plane but curved at the end. Okay, you cannot draw the circular, otherwise they will give you wrong. Okay, so depending on the slit size there. All right, so things that affect the diffraction. Now, you know diffraction is a spreading, right? Spreading of the waves. We want to know what change and what does not change. Let's talk about the wavelength. Does the wavelength change? No, it doesn't change. Before and after is the same. Does the frequency change? Frequency also remain the same. Same. So if the wavelength the same, the frequency the same, then the speed must be the same. Okay, speed is also same. What else? The amplitude. Does the amplitude change? Answer is yes. Amplitude represent energy. So if amplitude drops, the energy also drops. During a diffraction, the amplitude decreases. Why? Because if you just think of it logically, when the wave goes to a wider area, okay, when a wave goes through a wider area, it's kind of like the energy is being dissipated into a wider area. So that means one point is going to have less energy compared to one point in the region before the diffraction. What I mean is like this. If I take one point here, let's call it point A, and another point here, B. Before the diffraction, it is traveling in this region, right? This region here. After the diffraction, they go spread out, right? So you have like a bigger region. So the total energy is the same. If you compare these 2 points, A and B, the total energy is being dissipated into more areas after the diffraction. So that makes point B has less energy than point A. Take any point comparing before and after. The one after the diffraction will have less energy compared to before the diffraction. You can think of it like, let's say 1,000 ringgit share among 100 people. each person get 10. But if 1,000 ringgit share among 1,000 people, each person only get 1 ringgit, right? So the energy at one point decreases. Okay, so the energy here, amplitude decreases, energy decreases after a diffraction. Okay, now we want to know what affects the diffraction. First, there are two things. One is the wavelength. Second is the slit size. The longer the wavelength, the more the spreading, the more the diffraction. So red light, longer wavelength than blue light. Red light is going to diffract more. Blue light only diffract a little bit. Second one is the slit size. The smaller the slit size, the more the diffraction. Can we say the smaller the slit size, the stronger the vibration, the diffraction? You see, let's say we have a wave coming at a certain wavelength. Okay, and then we have a slit that is bigger. Let me draw it wider apart. Okay, we have a slit that is bigger than the wavelength. Okay, whatever the distance here, distance is bigger than our wavelength. Is that diffraction? There's still diffraction, yes, but it's very small, just a little bit. Now, when we decrease the slit size, we decrease it to same as the wavelength. Okay, the diffraction is going to be stronger because you decrease the size, the spreading is wider, and you get circular waves, right? What if I decrease the slit size more? I decrease it until it is smaller than the wavelength. D2. D2 is smaller than wavelength. What happens to the diffraction? Is it going to be stronger or weaker? Now, you see, when you decrease it down to smaller than the wavelength, okay, the angle is wider, yes. The angle is wider than the previous one. Whatever the angle here, theta 1, this theta 2 is going to be wider, spread more, right? But at the same time, the energy also decreases tremendously, right? Because you are getting more area, so the energy drops even more. So is it fair to say that the smaller the slit size, the stronger is the vibration? Can you say that the vibration here is strong because the energy at each point is getting even smaller and smaller? Okay, so that means in between there, they find a balance. They say that, okay, decreasing slit size, increase diffraction, yes, that's not wrong, but there's a limit. You cannot decrease down, so decrease down to too small, and then your energy become too small. Okay, the energy to be become too small to be recognized, to be noticeable. Okay, so from there they find a balance. There's a limit. You cannot keep decreasing like that. So they conclude that the strongest diffraction, the strongest, mind the word, the strongest, is when the wavelength is equal to the slit size, which is the middle one. Okay, they say that this is the strongest diffraction, because you have to look at the spreading. Not only the spreading, you also have to look at the energy spread. Okay, the energy decrease. Right? So in your real life, where do you see diffraction? What is the use of diffraction in real life? You see the harbor wall, okay? They built the harbor wall to have a narrow opening. What is the reason? So you have, when the violent wave comes from the ocean, it has high amplitude, right? So as it goes through the opening, they are allowed to diffract, and that decreases the energy and preventing the violent wave from destroying the boats. Okay, but there's again, they have to decide how narrow is it. How narrow? Cannot be too wide, because if too wide, the energy is still very large. And as the wave got in the harbor, it reflects. It reflects again from the shore, okay, from other obstacles. So the energy kind of bounce back and forth inside. Okay, so they don't want that to happen. So they decrease, but they cannot be too small also, because if the opening is too narrow, it's very difficult for the boat to navigate, right? It's very for it to navigate through the opening. Right, so from there again, they find a balance. So that is one application of diffraction of water waves. And you also see with the narrow boat, okay, with a narrow boat, let me draw like this. Say this is the boat, and compare narrow and wide one. Which one has more diffraction? We have two boats here, boat A, boat B. The one narrower will have a greater diffraction here. Okay, when the wave goes round the corner, it got diffracted right here. And as the wave from top and bottom diffract, they meet here at the middle section, they interfere. Okay, the interference of wave forms constructive, destructive. And as a result of that, you get very violent wave. You get some wave that are constructive, double the amplitude. But with a wider boat, wider cross-section area, the wave diffract like this, and diffract like this, and they do not meet because the cross-section is too wide. And if they do not meet, they do not interfere much. So the water wave behind a bigger boat, or like a big boat, a ship, okay, is not that violent compared to a smaller boat. Again, this is one of the things that you see on the diffractions. Diffraction of sound waves. Okay, sound waves. What is the range of frequency that we can hear? Sound wave range of frequency. We can hear human audible hearing range is about 20 hertz to 20,000, right? 20,000 hertz. Now, the speed of sound in air is 330 meter per second. Let's just assume that it's at standard conditions. Of course, it changes, depends on temperature. Okay, so we have the speed, we have the frequency, and we can calculate the wavelength, right? So V equals to F lambda, wavelength equals to V over F. So 330 divided by 20. What is the smallest wavelength? 330 divided by 20, about 16.5. What about the upper limit? You take, okay, wavelength equals to 330 divided by 20,000. Oops. 0.0165. 0.0165 meter. Okay, so in between 0.0165 meter, which is the upper limit, and 16.5 meter, which is the lower limit, that is the range of the wavelength that we can hear. Now, if you see this range of wavelength, 16.5 and 0.0165, your surrounding, like the doorway, the distance between one building to another building, or any hallway, any obstacles, their distances is about in this range. So that makes sound wave in our surrounding diffract easily. Okay, that is why you hear sound from the corners. Okay, in other side of the corners, still you hear the sound because the sound is actually diffracting around us. Everything around you, they are the distances between obstacles is almost lying in this range between 0.0165 to 16.5 meters. Okay, so you have the sound can diffract easily in our surrounding. Now, Other applications such as, again, sound wave, like in the concert. If you see the concert on the stage, what they use like long speaker, right? They use very thin and then tall speaker. Okay, they don't use like short and wide speaker. Why? Because they use tall speaker so that they minimize the vertical diffraction. Okay, because if they use short speaker, the diffraction is more, vertical diffraction is more, because the opening is very, very small. So that means if the diffraction is more, then the sound wave travels to the ceiling and then got reflected off the ceiling, and you hear many echo. You hear many echo in the concert. So that's why they use a much longer speaker with narrower width. Okay, narrow width is because they want to maximize the horizontal diffraction. Okay, so smaller width, smaller slit size, more diffraction, and then they use longer, taller speaker so that the vertical diffraction is not that much. Again, they minimize the reflection of the ceiling. Okay, that is also one application of diffraction. Radio waves, microwaves, radio transmission. Okay, the radio transmission, as they usually use long wavelength. Okay, they use long wavelengths, and longer wavelength, what happened? They diffract easily, right? So longer wavelength diffract easily, that means it's very easy to pick up the signals over the hills, okay, over the mountains, or over at the side of a building. All these hidden areas, they can pick up this signals because because the radio wave, they can diffract to all these corners or these hidden areas. Okay, like for example, if you have things like this, let's say you have, okay, this is the transmitter, and you're over here. Okay, it sends out the wave and diffract around the corners, then all these hidden areas, they can also receive the signal. But television or the FM radios, they use much shorter wavelength. They use wavelength that is like almost near the microwave region. So if the wavelength is much shorter, that means less diffraction. Less diffraction, that means there are some regions, there are some places where they have no access. They cannot detect, they cannot pick up these signals. So they have to install like a relay station, okay, something like a tower to help in transmitting the signal in every corners. Okay, so these are just a few that we see around us, okay, that uses the diffraction. Okay, now go to the next one, which is the interference and the superposition. Now, when wave diffract, if you have two sources, they interfere. What is interference? How do you describe or how do you define interference? Interference of a wave is a phenomenon occurs when two waves meet to combine, to form a combined effect. Now, never confuse interference and superposition. Okay, you see here, interference. What is interference again? It is a phenomena. It is an event, okay? A phenomena occurs when two waves meet to produce a combined effect. Then what is superposition? Superposition is when you want to find this combined effect. How are we going to find a combined effect? Let's say you have a crest coming like this, and then you have another crest. coming like this. This one has a certain amplitude. This one has a certain amplitude. When they join, how do you find a combined effect? Based on the principle of superposition. Okay, the principle of superposition, it says that to find the combined effect, we are going to add the amplitude together. So this one plus this one, you get a double amplitude, 2A. This principle is this method of finding the combined effect is based on the principle of superposition. So that is different from interference. Interference is the phenomena itself. But how do you find a combined effect? That is based on the law or the principle of superposition. Okay, so be careful when you define it. So how do you define the superposition? Superposition, you say, okay, it states that the combined waveform is given by the sum of displacement of individual wave. Okay, the combined waveform is given. State that the combined waveform is given by the sum of displacement of the two individual waves. For interference to happen, there is a condition. What is this condition? That is, the two waves must be coherent waves. What is the meaning of coherent wave? Coherent means you can, okay, just put it simply, it is same frequency and also same wavelength. Okay, the two sources must have same frequency or same wavelength. How do you achieve same frequency and same wavelength sources? The easiest is you just take one source, such as a laser that goes through two opening. You create two sources which has same frequency and same wavelength. Okay, instead of using two sources, you only use one. The easiest way to create coherent waves. Now, talking about creating coherent waves and also the phenomena of interference, we will look at one of the very famous experiment, that is the Young's double slit. Okay, now the Young's double slit experiment is used to prove that light behave as a wave. That's it. If you are asked, what is the purpose of Young's double slit? Just one sentence: to prove that light is a wave. Okay, to prove that light is a wave, and also to allow you to calculate the wavelength of light. Okay, any light, not the visible light, the electromagnetic spectrum. Okay, very early age, when he started his experiment, he uses a candle instead of a laser. Before there's laser, he uses a candle, and a candle gives off white light, correct? And white light contains 7 colors. And first, this white light is allowed to pass through a single slit first. Okay, so when the white light passes through a single slit, the white light diffracts, and then the diffracted wave is again allowed to pass through a double slit. Why do we need 2 slits? Why not just take the double slit? Because the first slit is to produce a coherent wave. You see, when the white light goes through this one, you got red, blue, violet, all colors, right? But they all have different wavelength. The longest wavelength diffract the most. So red will be at the edge. Red will be the one that diffract the most. And then you have orange, okay, yellow, green, blue, followed by until violet. So let's say blue is less diffracted compared to the red. And this double slit, the slit size is almost the same size with the blue wavelength, the blue light. Okay, the wavelength of the blue is approximately the same size as the slit size. This one, it's not exactly the same, but it's a comparable size. Okay, so that means only the blue can diffract through the double slit. The other colors, they are blocked. Okay, so the function of the first slit is that it creates many colors, but only the blue can go through the second slit. So what happened is that we have created a coherent sources, because what's coming out of here is just blue. This one is just blue. Same wavelength, same frequency. Okay, so this is how the Young set up his experiment. But then nowadays, we don't use candle anymore, right? We use what? We use laser, because we already have lasers, monochromatic light, that only sends out one light. So we can actually eliminate the first part of it, and we just use a laser straight away to the double slit, like this. Okay, now let me draw a bigger picture here. Okay, so we have one here, one here. Now here is the screen. Okay, so two coherent sources coming out from the double slit. Now this double slit, let me draw a distance here. Let me see. One wave from here travels to this point, and another wave from here travel to this one. We pick a point here, but in reality, all the waves, they fall on every single point, right? So we just want to analyze this central point here. So this central point here, now you see here, the distance traveled by the first source and the distance traveled by the second source is the same, because we're taking the symmetry of this. Okay, so both waves, they travel the same distance. Okay, when they fall on this one, they interfere and they form a bright fringe, a bright fringe. Okay, a bright fringe. Now they started at the same distance, same point. They started at the same point. They travel the same distance. That means the path difference. The path difference is 0, because they travel the same path, so there's no lagging in behind. They arrive at the same time. In other words, the path difference or the phase difference is 0 when they arrive at the center here. Okay, yeah? So you can think of it like this. If I have a wave that goes like this, and we also have a wave that goes like this. When they reach here, they have 0 path difference. So the crest coincide exactly with the crest of another wave. Okay, that is the center maximum. This is we call the central maximum. Okay, so what is happening at the central maximum? It is where constructive interference is happening. So crest join with crest, or trough join with trough. Now let's pick a point somewhere down here. Let's say somewhere up here, you see another bright fringe. Okay, if I draw the path that the wave travel, one here, another one from here to here. The first one traveled this distance. The second one traveled longer distance from here to here. It's longer than this one. So if I draw a line like this, this is a equilateral triangle from here. That means if this distance is the same as this one, that means this is the extra length. Whatever this length is, right? This is we call the path difference. This second source, source 1, source 2, second source has to travel a further distance of whatever this distance is. And then as it arrives at this point, okay, they are not going to be exactly in phase. Okay, so depending on the path difference here, of course, depending on this path difference, if this path difference equals to lambda, the wavelength of the wave, then what happened? You see, one wave like this, and then I have another wave like this. This is zero path difference, right? But if the yellow one and the blue one, these two waves, if they have a path difference of one wavelength, that means one is lagging behind one wavelength like this. So again, the crest meet with the crest. It is still a constructive interference. Okay, so if the path difference is equal to one wavelength, again, a constructive interference takes place over here. So you get another bright fringe. If the path difference is like this, what is this path difference? This is half a wavelength. Okay, this is half a wavelength. You take one point here, measure this one. This is half a wavelength. So if the path difference is half a wavelength, or you can also say that the phase difference, okay, the phase difference is 180. This is 180 phase difference. Destructive interference take place. And where is the path difference of half a wavelength? It is between the two bright fringe over here, where you get the dark fringe. Okay, now, when question asks, what is happening here at this point here, the bright fringe here? Okay, explain how a bright fringe is formed. You mentioned about not only you mentioned constructive interference, you also mentioned about the path difference. Okay, you have to include the term path difference or phase difference. So you talk about the path difference is one wavelength. Now, other than one wavelength, it can be two wavelengths, right? Because if it's lagging twice, the crest still meet with the crest. Okay, if I draw the wave like this, we do like this. Okay, one wave, another wave, zero path difference. If I bring it to the back like this, this is one wavelength path difference, and I bring it again like this. This is two wavelength, but it's the same. Two wavelength, one wavelength, and zero, they're all the same. The crest meet with the crest of another wave. So all of this, they form constructive interference because the crest with the crest. So whether it is one wavelength, two wavelength, three wavelength, four wavelength, is all constructive interference. This one you have to remember, take note of this. So I write down here, bright, how is it formed? Whenever the path difference of the waves is zero wavelength, two wavelength, three wavelength, four wavelength. Or in general, I can write m wavelength, where m is an integer, a numerical integer. So this all, or you can say in terms of the phase difference, sometimes they ask in terms of phase difference, then you give zero phase difference. One wavelength is how many phase difference? One wavelength, the phase difference is 360, right? 360, two wavelength, so it will be 720, and keep on going. All this phase difference, they form constructive interference, the bright fringe. Okay, so the bright, second bright, and then the third bright down here. All this, you have many. So we call this one the center, So we'll let the n be 0. This is the 0th order. N equals to 1, the first order, the second order, n equals to 2. Same down there. It's symmetry. Okay, the same down here. What about the dark fringe? For the dark fringe to form our phase difference, okay, let's talk about the path differences. The path difference needs to be half a wavelength, right? So we have half a wavelength. That is when this one lagging like this. Then you have the crest meet with the trough. After this, the next one is like this. This is 1.5. Okay, so we have half a wavelength, 3/2 wavelength, that's 1.5, and then 5/2 wavelength, and then carry on with 6/2 wavelength. All this form the dark fringe, the destructive interference. Phase difference. You just convert all this into angles. Okay, so phase difference for this one is 180, right? 180, and then you go carry on with this one. You just convert it to angles. Now, the pattern for this one, we have m plus 0.5 and then wavelength. Okay, let me change this to n. And this one also, I change this to n lambda. So let's say it is the seventh dark fringe. You want to find out what is the path difference of the 7th dark fringe, the 7th order. Okay, just put 7 inside here. Okay, 7 plus 0.5, and then times the wavelength. You get the path difference of that order. If it's 0, the central maximum. So this one n is 0. This one 0.5. This one 0 is actually referring to the one next to it. This one, the dark fringe. Okay, because the central one is the bright. Okay, it could be this dark or the down here, the dark down here. This one and this one, their path difference is half a wavelength. Okay, so when you put 0 here, you get 0.5 here. Okay, example. Let's say the question says, okay, there's a wavelength of light, let's say microwave. Okay, there's a source of microwave with a wavelength of 0.025 meter. And it goes through the slit. It forms a bright fringe. Okay, let me erase this first. If you want to take a screenshot, then you can take it very quickly, and then I will erase this. Okay. Right, so a microwave source goes through the double slit, and then the microwave diffracts, and then you get, they have a detector here. They put a detector here to detect the intensity of the microwave. Okay, and then they say that, okay, I start from this position and I sweep through this distance to the next point where they observe there's again an increase in the reading of the microwave. So that means the central position, it must be a maximum. Okay. And then at this position, also, it is a maximum. Suppose that this distance here is 0.75 meter and this distance here is 0.90 meter. And the question asks you, as the detector sweep through this distance, how many spike in the signal, or how many maxima is detected by the detector? Okay, or they can ask, describe what is the reading of the detector as you sweep through this distance here to the next bright fringe. Now this bright fringe, not necessarily it is the next one. It could be further down, right? It could be the 6, the 7, the 9. It's not stated here. So how do you find this one? How do I know that this is which order is this one, the bright fringe? You have to look at the path difference. Okay, you look at the path difference. So that's why the length is given here. Okay, again, how to calculate the path difference? We take 0.75, 0.90. So we calculate, okay, path difference 0.90 minus 0.75. We get 0.15 meter. Okay, the path difference is 0.15 meter. What is the wavelength? The wavelength is given here, 0.025 meter. We want to find what is the path difference in terms of wavelength. Okay, we know the path difference is 0.15, but how many wavelength is that? We divide it. So path difference in terms of wavelength, we take 0.15 divided by 0.025 equals to 6 wavelength. Okay, so we got this. 6 wavelength is the path difference. Right, then using the m lambda, okay, for constructive interference, m is the order, okay, lambda. So we put in here. So we know that m is equals to 6. That means this bright fringe over here is the 6th order. Okay, so if this is the 6th order, this is the 0th order. How many orders in between? So you got 1, 2, 3, 4, 5. What is this order? The order is the maxima. It is the bright fringe. Okay, it is the bright fringe. So how many bright fringes in between? 1, 2, 3, 4, 5. You got 5 bright fringes in between the first and the last one. If you plus the 2, its total is 7. So as you sweep the detector through from the 0 to the 6, then you will have 5 times spike in the signal. Okay, because in between there's 5 times of rising, falling, rising, falling, rising, falling, rising, falling, like this. Okay, all right, now let's have a short break and we come back to continue with the diffraction grating. So we'll come back at 7:55. Yep. Okay, so guys, we continue. Right, so diffraction grating. It's actually the same as the double slit, just that we change the slit. Instead of using two, right, we use many small slits, okay, that we call it the grating. Okay, we can do it like this. And usually, this grating is like, they will call it like how many lines per millimeter. So the grating looks like this. You have a piece of it, and then you have the very tiny lines. Is actually the slit. How they would measure the slit is that they would measure like 1 millimeter and how many lines in 1 millimeter. Okay, so they calculate how many lines per millimeter. So they have, like, for example, 300 lines per millimeter. They have like 600 lines per millimeter. Okay, so in 1 millimeter, there are 300 slits, very small slits. So when the light is shine on it, the light diffracts into all of the slits. Okay, the phenomena behind it is the same as the double slit, just that the difference between the diffraction grating and the double slit is that the diffraction grating is actually better if you want to calculate the wavelength. Okay, if you want to calculate the wavelength, the diffraction grating is better. Why? It's because diffraction grating, when you shine the light on it, and then the light that you see on the screen is actually brighter than the double slit, because you are letting more light go through it. So if the maxima is brighter, that means it's very easy for you to take measurements. Okay, so how they calculate the wavelength from the experiment? They would do like this. They shine the light on it, and then you get the central maximum, and you get the higher order, right? Order 1, order 2. So they measure the distance here. Based on the next bright fringe, what is the distance here? Okay, x2. And what is the distance here? x1. x1 would be the distance from the grating to the screen. Okay, once they get this experimentally, and they can calculate the angle using the trigonometry, right? So once they get the angle, then using a formula, d sine theta equals to n lambda. Okay, so this is the only formula you need in the diffraction grating section. Yeah. Now, once you have the angle, you have the order as well. Okay, the higher order, this one is order 1 or order 2. And also you have this d here. What is this d here? This d is the slit width. Okay, slit width. That means, example, if we use 100 lines per millimeter, okay, we use this grating, then what is the slit width? We calculate using, in one millimeter, you have 100 lines, right? So slit width is you want to find the distance between the lines. Between the lines. So if you have 100 in 1 millimeter, so the slit width is you take 1 millimeter divided by 100. It's equals to 0.01 millimeter. Be careful with the unit. After you divide it, you are still in millimeter. So you want to change it to meter. So 1 times 10 minus 5 meters. Here you get the slit width. Okay, that's how you get the lowercase d here. Okay, so once you have this, then you can, no problem, you can find the wavelength. Okay, now a few things to take note when you do the experiment is that you have to make sure that this screen, the grating, must be parallel to the screen. Okay, grating parallel to screen. or this incident wave or the incident light must be perpendicular to the grating. You cannot like make an angle with the grating like that. Otherwise, it won't be accurate. If this is tilted like this, the grating is tilted like this, such that it makes an angle with the incident light. How will it affect the experiment? You will get that this light, the bright fringe over here, right? This is the first order, and under here, this is also the first order. By right, this should be symmetry, correct? By right, this should be symmetry. But because this is tilted, and it would affect the distance here, so you will see that the bright fringe, the upper one is not the same as the lower one. Okay, so if the question asks what are the precautions to take note, take note when you do this experiment, then you talk about this one. Has to be perpendicular, and the grating has to be parallel with the screen. Okay, so let's say we want to find the wavelength of this light here, whatever is the wavelength here. So we do the experiment, then we get the order. You get this central order, okay, n equals 0, first order, second order down here, and the higher order. Actually, in the actual case, they use a curved screen, so that they see the higher order. If yours is a flat screen, then the higher order is very difficult to see. Okay, so the order is only representing the maxima. The minima is not shown here. It's in between the maxima. Okay, so take the higher order, because the higher order is the one that's easy to measure. Okay, when you do an experiment, the first order may be too close already, so you want to take a second order or third order. Okay, so let's say we take the second order. So if n equals to 2, and we can get the angle. So let's say the angle, for example, is 50. Okay, what is the angle here? The angle is the angle with the central. So if you are taking the second one, that means the angle is over here to the central maxima here. Okay, not with the one, so all the way to the center. This is 50 here. Now, again, then we take the formula, lambda equals to d sine theta divided by n. Okay, 1 times 10 minus 5 sine 50 divided by second order. Okay, what is this? Okay, get 3.83 times 10 minus 6 meter. Okay, so what's the purpose of diffraction grating? To calculate wavelength. That's the main purpose. Same as the double slit. Okay, they give the same result. Right, so what about the intensity? Okay, intensity. Now, and intensity, of course, the middle one is going to be the highest intensity. So if I plot the intensity graph, central one will be like this. This one should spike the highest, and then this one slowly taper off like this. This, like this. Okay, you can see the maxima should have a spike in amplitude, and the minima is 0 amplitude over here. 0, 0, 0, and 0. So when you go up higher order, the intensity decreases. And also in L levels, we know that intensity, we use what one simple expression, intensity is proportional to amplitude square. Okay, so let's say, let me give you one example. How will they ask the intensity? For example, they ask you to find, okay, what is the ratio of the intensity of the maxima over the intensity of the minima? Usually they will ask ratio because you can't really calculate exact the absolute value since you only have this directly proportional, right? You don't have a equation for that. So usually they will ask you ratio. So intensity maxima, okay, suppose that the maxima, you got two waves arriving at the maxima. One wave is having an amplitude of 6 cm. Okay, just an example. And then you have another wave that interfere with it that is arriving at the same place but amplitude of 2 cm. Okay, so then here, when they arrive at the maxima, this is where the constructive interference take place, right? So to calculate the intensity, so you want to total up the amplitude because this two is going to interfere, right? They interfere, they superimpose, you get the absolute amplitude. So 6 plus 2, okay, 8 cm. This is the total amplitude at the maxima. And when the same two waves interfere, okay, at the minima, okay, at the minima, the same two waves interfere. So what is the amplitude? Absolute amplitude equals to 6 minus 2 equals to 4 cm. Okay, this is at the minimum. So you do the ratio I max over intensity at the minimum equals to 8 square over 4 square equals to 4. So it's about, ratio is about 4 times of the intensity at the minimum over here. Okay, so it's kind of like the ratio of the middle one with the ratio of the one next to it, the dark fringe and the bright. Okay, what if the question asks, okay, provided the wavelength is the one we calculated to 3.83 times 10 minus 6 meter. And it says, okay, find how many numbers of orders that you can see. Okay, find the max order observed. Oops. Okay, then we'll use the same thing. D sine theta equals to n. So we're going to write n equals to d sine theta over wavelength equals to the slit width is same, so 1 times 10 minus 5. Now, to find the maximum order, right, we are going to take the angle as 90 because the maximum the angle can go is 90, right? It cannot go 90 maximum, you cannot go above 90. So if you want to see how many orders in total, we are going to take angle equals to 90. And just to find out how many n, right? So if I put 90 here, sine 90 divided by the wavelength 3.83 times 10 minus 6. This thing become 1. Right? So you have the sine graph here. This is 180. Here is 90. This value here is 1. So sine 90 equals to 1 equals to divide this one. So we get 2.61. Okay, so the n is 2.61. So what is the answer? Can it be 2.61? There's no 0.6 order, right? There's no 0.6 order. 0.6 means that you cannot see the third order yet. You cannot see the third order. So the maximum that you can see is just 2. So we round down to 2 orders. Okay, maximum is 2 orders. So it's kind of like the central, the first, the second, 1, 2. Don't forget you got the other way, the other side. You got 1, you got 2 also. Okay, so total how many bright fringes you see? 1, 2, 3, 4, 5. 5 bright fringes. get some space here. Okay. Okay, what if I, instead of shining one wavelength of light, I shine white light? What will be observed on the screen here? Okay, you see, white light has 7 colors. So the central must be white because all the colors come together at the same point. So you get also white. So central maximum is also white. How about the first order? If you look at the first order, because you have many colors, right? Many wavelength. And also different wavelength, they diffract at a different rate, at a different angle. Okay, so if you see the formula here, d sine theta equals to n lambda. When we take, this is constant, so the grating we don't change. Okay, we don't change, same as the previous one, and the order is also the first order. Okay, so this two is constant. We're analyzing only the first order. So what happens when you change the wavelength? If the wavelength is high, that means the angle is going to be high as well. Okay, so the higher the wavelength, the more the angle. So higher wavelength, they tend to diffract more. So their bright fringe is formed at a distance further away from the center. Okay, so that means what you will see is this. First, maybe you'll see blue. Okay, blue forms here. Oops. Oh, that is a freehand drawing. Okay. This one, blue. Blue. And then the next one, maybe you'll see yellow. Why? Because yellow has longer wavelength than blue. And after yellow, maybe you see, okay, red light. Over here, we form here. Okay, so blue, yellow, red. Okay, by right should be violet first, right? Because violet the smallest wavelength. But I'm just, okay, you get the point. Okay, I'm just showing 3 different colors here. Okay, so blue, yellow, red. Because the longer the wavelength, the greater is the angle. So that's why you see red is at the furthest away compared to other colors. So you kind of see this colors split out when you shine a white light, right? You shine a white light through the diffraction grating. On the screen, you see a rainbow. You see a rainbow color. Okay, huh? Another way to achieve it is by dispersion, right? So you like take a pail, you fill it with water, and then you take a mirror. It's like the experiment we did back then in high school, right? So you put the mirror underneath, and then you see a rainbow on the wall, reflected on the wall. So that one you can also achieve it. This is by refraction. That is by refraction of water. You get the rainbow. But this one is by the diffraction and interference of light. You see the rainbow colors. Different phenomena, but same result. Okay, so same down here. The closest down here would be, okay, blue, then red, yellow, then we have red here. Boom. Blue, yellow, and we have red. These are all the first order. Okay, so this is central. This is first order. The first order for red, blue, and yellow. And again, this is first order for red, blue, and yellow. Each order, you get 7 colors. So the second order, you get again the seven colors. Because we are dealing with here is the source has 7 constituents. Okay. The same thing you see the underside of the DVD. Have you ever seen the CD, the DVD? There's 2 sides, right? The underside is where the player reads, right? If you look at the underside, you see like rainbow colors. When you put it under the white light, you see this rainbow colors on the disc. That is actually same principle, based on the same principle, which is diffraction grating. If you zoom in, you take a very microscopic view of the DVD. The surface is not entirely flat. It's not entirely flat. There are some regions where it is slightly raised. They call it the pits. Okay, so basically you have a CD like this. This is the CD, like a DVD player. And then usually the top side, they have the cartoon and stuff, right? But the underside is the silver color one, right? So they have, if you zoom in, they actually have very small pits. This is areas where it is raised up. It is slightly raised. So when you have a slightly raised stuff and they actually shoot a laser onto it. They shoot a laser onto it, just like your diffraction grating, you shoot a laser to the grating, right? They shoot a laser under the player, they shoot a laser to the surface. And then what happens is that all the laser will be reflected. And as it reflects, it diffracts at the same time. Because remember, diffraction not only go through a slit, it can happen also when it hit an obstacle, right? So these are like the obstacles. So when the laser hits it, it diffracts and it reflects off the surface. That's why you turn the CD, you look at the underside, you see like a rainbow color. This is the same principle here. It is also diffraction grating. Okay, and based on this rainbow, this colors, right? The orientation of the colors, the electronics in the player convert it to information that we don't need to know that. That is a very complicated process. Okay, and that is one use of it. Another use of diffraction, okay, like this one, the white light coming through, split into rainbows, right? Why is this important? They are used in astronomy, right? In astronomy, how do the astronomers, they study the composition of a star? For example, how do they know sun is made of hydrogen, helium? How do they know? They study the light that is coming from it. Okay, they study the light that is coming from it. So the light, the starlight, come here, and then they put a grating to capture the light. This is the grating. So when the light goes through it, it diffracts. Just like this one, it shows all the colors. By analyzing the color that is missing, they are able to tell what is the chemical composition of the gas of the star. Because certain gas, they absorb certain colors. Some gases, they absorb certain wavelength. Other gases, they absorb certain wavelength. It's kind of like this. This is the gas, right? It's like a gas cloud. When you have a light that passes through it, and then you have 7 colors of light pass through it. And coming out from here, maybe only 4. The 3 colors already absorbed. So the astronomer, they pick up this one They pick up this light, they let it diffract, so they see all the colors, right? They see, but they only see the 4. Where are the 3? The 3 missing colors. Okay, then based on the 3 missing color, then they can know what is this gas made of? What is the composition of this gas? Because they actually know based on a certain gas what color they will absorb. Okay, for example, like hydrogen gas, what color they will absorb. They already know. Okay, oxygen gas, what color they will absorb. So based on the missing colors, they can tell, okay, is this hydrogen, is this oxygen, is this what? So this is how they use to study the composition of stars in outer space, because you can't actually go there, right? You can't actually go there to study the what is it made of. Okay, you can only look at the light, analyze the light. Okay, so here's a short lesson on the diffraction, and we finished the